Welcome everybody. Thank you for the CCH for organising this. It's really a pleasure to be here. We had our own little event at ARM, and this is great to bring some of that here. So, Sophie, what's it like to be looking back on 40 years?
It's like being 40 years older. There's a lot less hair among my colleagues. And otherwise, some of the events are fresh and some of the events are dimmed by the mists of time. And I suppose more importantly, some of the events are overlain with false memories from other people's stories that were wrong.
We know who you were looking at.
No. Steve is exemplary. He accepts correction, but Hermann Hauser is a spinner of tales.
So maybe we could go back to kind of just a little bit before ARM, and talk about kind of the BBC Micro and how your sort of contribution to that. We had an interview here with Chris Curry, and he said that your code was kind of always spot on and worked first time. And do you think you have a particular mindset that a particular way of working?
We were always aware that we were costing people money with what we did. So something like the Acorn System 1, that was a computer built in the times before there were development systems. So there were no assemblers. Everything that I coded for that machine was basically by writing it on A4 sheets of paper in assembly language, hand assembling the assembler to binary, and in the case of the Acorn System 1 monitor, taking my binary and putting it into Nick Toop's prom blower at Science of Cambridge and blowing the proms. There was a high and a low prom, so I think there were 256x4s for the very first prototype, would be 512x4s for the production machine, and programming all those bits in, taking the proms out of the prom blower, putting them in the actual machine and having it work. Now that's reliable. People are overly impressed by that sort of thing, but when you're spending other people's money on stuff, and some of the stuff is virtually irreplaceable, there are a limited number of proms and a limited number of attempts you can make, so you just have to get it right. So that,
as much as anything, then it was those limitations, those constraints that sort of forced you to get things right, to think through stuff.
I think they forced into everybody the need to know what you were doing and do it right. So everything that we knew in Acorn, we developed ourselves. It wasn't like you could open a manual like you can today on how to design processor instruction sets, or that chips came with development systems or disks or downloads on the internet, because none of those things existed. So if you bought a 6502, you bought a 6502. You would then go off and buy the data book. And later on, when we had Acorn System range machines, I would write an assembler for them. Replaced later by a better assembler, but I wrote the first one. And that took the handwork, the painful stuff out of doing it. But of course, that assembler I wrote, how big was UA? About 2 or 3, 4K, something like that. I wrote 4 kilobytes of code, about 2,000 instructions to get an assembler that worked and did anything. And that had to be written by hand, it assembled, because there wasn't an assembler. And then I had to write an editor and all that sort of stuff.
And so that's something I've kind of observed. How many elements of that system you contributed to? How many different aspects of it you were involved in? Is that something that's sort of stood you in good stead for then thinking up the instruction set?
So Herman came and found both Steve and myself from the Cambridge University Microprocessor Society. Is that true for you, Steve? Yeah. He just plucked us out, and we were individuals who fulfilled a need that Herman wanted. So in my case, I was the person in Cambridge University Microprocessor Society who knew everything about low power electronics, because I bought the RCA CMOS data book, the one called COSMAC from 1972, and ingested the whole thing and memorized it all. And then when Herman wanted something that used low power electronics, I could build that sort of thing. But the first job I did for CPU Limited was that Steve and Chris Turner had built a dual processor SCMP controlled fruit machine. I might have to go the other way on this picture set. So they built this fruit machine, and ACE were very worried about people with newfangled piezoelectric lighters for cigarettes, and coming up beside the fruit machine, doing a piezoelectric lighter thing, striking a flame, and disrupting its complicated electronics. So ACE wanted our assurance that it wouldn't do that, and that suddenly, for reasons I've never quite understood, became my job. I had nothing to do with the fruit machine in general. I mean, all of the SCMP guts would be ripped out and replaced with 6502s given time, but the SCMP one I knew nothing about. But what I could do was to look in Chris Curry's desk drawers, find sample chips that he'd been given by various companies to do various things, and I found, I was about to say Motorola, but I think it was actually Signetics. I found a wideband RF receiver chip that's supposed to be a single chip radio, and so I could implement something, and I took all the tuning components off the circuit from the data book so that it would be utterly as wide a spectrum as the chip could manage. So when it detected a strong signal, it gave a signal out that reset the fruit machine controller. So all of that worked in theory in my head. When ACE wanted to test that fact, they took the machine down to their factory floor, plugged it into a socket outlet on the factory floor, plugged an arc welder in next to it, and started striking sparks. Neither Steve nor myself saw this, but Chris Turner did. I'm retelling other people's stories. And the machine survived, and CPU Limited, as it then was, got the contract.
That's quite a lot more than a cigarette lighter.
Yeah, there's a certain amount of luck in this as well.
Is that an example then of you turning your hand to something that's quite... I'm assuming you hadn't done sort of RF electronics before, or perhaps you had...
Well, I'd built a radio before.
Right.
I built a radio out of transistors.
Okay. So
So I sort of knew what I was doing, but only sort of.
Yeah. But you were game for the challenge, and you could work your way through the data sheet, and...
People pointed at me and I did it, so there we were. So, I mean, obviously after that came the Acorn System 1, which is the thing I was just talking about, the monitor. So, originally I was employed by Herman to do the hardware stuff, and it sort of went sideways into doing software as well. I mean, this is obviously a real one. I have the Hawk prototype of this machine at home still. So System 1, well, it got the company hooked on the 6502, which was obviously my favourite microprocessor at the time. Everybody in the Cambridge University Microprocessor Club seemed to like a different microprocessor. So there were some people who liked bit slice machines. So they talked AMD 2900 bit slice processing, and there are people who like TI 9900s, and there was me and maybe one other person who thought about the 6502. Steve was a 2650 man. There were some 6800 Z80 freaks. But this was obviously the best one.
Yes, it was.
And is this the machine that you would have first implemented BASIC for?
No.
No.
This machine, we started in a world where there were no home computers at all and no interest in them really. Horizon had made the TV program, The Chips Are Down, predicting the coming of the microprocessor revolution. And that's what got Herman, who was a physics PhD graduate, got him interested in starting a company that would exploit this coming stuff. But nobody really knew what they were for. And just having something like this, it became an element in control systems. So Acorn System range, if there was a focus for it, apart from Steve, myself and Chris Turner, all having fun building our own machines, the focus was on control. There was a company called Control Universal down in Harlow that we would go and visit when the M11 was first built, that wanted these machines to do industrial control with. And of course, the history of the company is completely changed when Chris Curry convinced Nick Toop to take some elements of the system range and an American NTSC video controller and make the Acorn Atom single board computer for proper home computing. And that had a port of Acorn System Basic, which I'd written by then, to be its Atom Basic. And then it had the Atom floating point extension ROM, and then I put that back into System Basic, so all the floating point stuff multiplied in there, and that became the ancestor of BBC Basic.
And the Atom then would have been the first machine that you could buy pre-assembled and you know, in a case with a keyboard and so on.
Well,
the first Acorn machine.
This was the first machine aimed at a sort of home user. You can buy it ready built, and you were definitely advised to do so, but if you bought it like that, it was a kit. And that meant that people would assemble an Atom incorrectly, shall we say?
We shall, very often.
Some people knew enough to be worried about soldering chips in. So we did have a machine back where they glued all the chips in because they were worried that too much solder would heat the chips up too much and they would stop working.
Oh, sorry about that.
And there was, you know, CPU Limited marketing itself as Acorn at the time. It didn't change its name for another year or two. We were a very small company, so there was a room upstairs in 4A Market Hill which would sort of pack computer kits in. We'd all stand, me, Steve, if Steve was there, Chris, Lawrence Hardwick, Pamela Rasp and Herman. We'd just go round the table putting components together in kits. And then, of course, we change roles and man the helplines. People ringing from phone boxes saying, "Hello, I have got an Atom, it does not work." And there was one guy who did that often enough to become a feature.
I think more people phoned up saying, "Why haven't you delivered it yet?" When I was doing the phones in the summer. Well, yes.
Yeah, so the Atom began to move us away from being a control company, but yeah, the Atom was shit. Wrong video controller, NTSC colour coming out of it, American TV standard framing instead of UK standard. If you had socketed the chips and built it correctly, then as you typed on the keyboard, the chips fell out into the box. It had a really poor linear power supply in the back of the case here, and it would get hot. And especially if you had the Atom extension RAM board in it. The whole thing was perilously close to the limits. The Proton, which would come next, was heavily influenced by how badly we thought of this machine. But at the same time, it was a groundbreaking change for the company as a whole.
Do you want to say something about then the computer literacy project, however you want to talk about that?
So, the BBC, when it made the Horizon programs on microchips, it didn't really know what it was doing. It was just making a single program. But there's a part of the BBC at the time, the continuing education part of it. Was that the right words?
That sounds familiar.
So they decided that this was important and they needed to educate the whole country in what was going to be happening. So that they said, right, we're going to have an internal thing, a computer literacy project that will push information to people. And at the time, all machines were different. Nothing worked from one machine to the other. They were built with different hardware and different software. So they rapidly decided that they would have to have a machine personalized to them. A machine that did everything that they wanted it to and would be suitable for educating people. So they decided to contract a company called Newbury, and after a while they began to realise that they were being late in delivering things. That's the best way to put it. And the Newbury New Brain machines didn't do what the BBC wanted, so the BBC decided that continuing education people in the computer literacy project decided that they would go round all the UK manufacturers and see if something could be done better and sooner. And we didn't really know about this. Acorn was probably too small and too unaware, but Chris Curry found out from a friend of his when he was visiting London that this was happening. So he managed to get his foot in the door and make a place for Acorn in the queue of people, on the basis that the machine that we were going to build, the Proton, which would be a proper atom, a professional atom, would be suitable for their project. So the BBC said, okay, you can be on the thing. We're coming to visit you on Friday the 6th of February. And we'd like to see it, please. So Herman rang me up and he said, well, I've got the BBC coming to visit and they want to see the Proton prototype this Friday. This was a Sunday evening. And I said, there is no way, Jose, that can work. Well, I probably didn't say Jose because it was Herman. And Herman said, okay, I'll ring Steve and see what he thinks and get back to you. Phone down. I was thinking, Herman rang up Steve. Steve, BBC are coming, they'd like to see a Proton prototype. Sophie thinks it can be done. Herman rang me back. I've been talking to Steve, and Steve says, yeah, it can be done. So we turned up on Monday morning, and this was before Steve was actually employed by Acorn /CPU Limited at all. So it was good of him to turn up. He could have been doing his PhD instead. So we rapidly discovered that neither of us had made those assertions. So the Proton was pretty much in our heads at the time. So we'd had meetings in Chris Turner's office and written down lists of things that we'd like the machine to do and had a sort of basic, rough block level understanding of what it would look like. But that was it. We had nothing else. So Steve spent a lot of time with Chris drawing a real detailed circuit diagram and started to get all the bits, because we wanted things like a 6502 that ran twice as fast as the ones we were using. We wanted memory that ran 4 times as fast as the memory that we were using and was larger. Hitachi's 16K by 4 DRAMs. We had a whole load of things that needed to be got, and got they were. By Wednesday, Ramanoush Banerjee, the fastest wire wrap gun in the West, came in from the computer lab to wire wrap the prototype, which could well be that, but doesn't look like it really. It doesn't look tall enough. That's not actually a prototype, but this sort of situation where we'd have an Acorn System range machine exercising the machine under test, a display connected to the machine, and all sorts of electronics, gubbins, oscilloscope, power supply, soldering iron. So built the machine an awful lot Wednesday into Thursday. Did the machine work? No, it did not. By 2 a.m. on the Wednesday morning, or stroke Thursday night, I said, well, this machine still doesn't work. If the BBC are going to see anything, I'll have to port some software to it in the morning, and I'm in no state to do it now, so I shall go home. I left the building, I went home, I had a very, very uneasy 4 or 5 hours sleep, came back in at 8 o'clock in the morning to find Steve, Chris and Herman asleep under the benches. And I woke them up and they said, well, the machine works now. Herman's story here is that we had the machine connected to an in-circuit emulator from a system range machine, so a big emulator that comes in and pretends to be the processor. And Herman said, well, if everything should be working and isn't, maybe it's the in-circuit emulator that's the problem. Take it out and put a real processor in there. And they had done that, and it did indeed work. So I spent a little time porting the system, operating system, to the Proton prototype and System Basic, and got a mode 0 display with a random line going by the time the BBC wanted to see it. So that they were overly impressed by something working as well.
So in my mind, that sets the scene then. You've got the people, the BBC Micro goes on to sell, I think, at least 1 million units. It seems to be in some... I'm amazed we don't know how many units. That seems to be lost, but certainly a lot.
It's anywhere from 1 million to 1.5 million,
indeed,
depending on who you listen to.
Yeah.
So yes, I don't know. I didn't count them.
So this kind of sets the scene. There's now kind of a good chunk of money. There's a team that's experienced in building a computer. You want to go on and build the next thing. Do you remember, what the aspirations were? What were you what machine were you imagining building? What was it going to be like? Was there a product marketing team setting a goal, or was it just an engineering machine for engineers?
So up to this point, everything had sort of been driven mostly by the engineers just wanting to build X, Y, or Z. And we'd done all of that. But now we had sort of proper stakeholders. Herman wanted the Proton to be an office automation machine. He'd been to America, he'd seen the Xerox PARC demos. He was convinced that the paperless office was going to happen. Chris Curry wanted a better home computer machine, good at games. Andy Hopper, then a director of Acorn, wanted a scientific computer. And I think the rest of us, the engineers, we just wanted something that made us happy and so on. So there had actually been big circles of discussion. How do we make this stuff? And the Proton is actually a multiprocessor machine. So you have the bit that you know as the BBC Micro is just the I/O processor part. So you cut the machine in parts. The I/O processor gets sold as eventually the BBC Micro, the home games computer sort of thing, successor to an Atom. You put on a 6502 or an NS16032 or an 8286, and you got a machine that was configured for different capabilities. You needed a 286 to run MS-DOS and be an office automation computer, and so that sort of thing. So it was a multiprocessor machine from scratch. We still had to build the tube that connected things together, but that was going to happen. So after all the trauma of getting that machine into volume production and all that sort of thing, you can't imagine what 1981 was like for us. We were all in the office on the day of the royal wedding. There was a Sony television over in the corner, and we were all working away on various software, hardware bits of the machine, trying to get things going. And it was like that the whole year until the first edition of the computer program at the end of 1981.
So it's basically a year to go from almost nothing in February, some ideas, to volume production in early 82.
Yeah, and that included building 2 custom chips.
That's incredible.
We did work quite hard. So after we got all of that stuff out the way, we started building second processors. And something became born on us very rapidly as we built all the second processors. If you looked at them, there was all sorts of marketing blurb about, particularly the National Semiconductor NS16032, how wonderful a machine it was and how it was going to revolutionise everything with its superior performance and extensive support for high-level languages. What we found was that all of the second processors had roughly the same performance if you controlled for the memory fetch bandwidth of the processor and built them all and normalised them to 4 megabytes per second. The performance was virtually identical. It didn't matter what the instruction set was. And Steve knew how to build a memory system that would run at 16 to 20 megabytes a second. So we started looking around the world for a processor that would do that would be able to use the performance of a memory system that we knew how to build. And we couldn't find one. And we did look quite hard, and we went and visited all these companies. Mostly these companies were big Silicon Valley tilt-up buildings packed full of hot and cold running engineers. And we went out to visit National. National was a big case in point. They wouldn't give us an NS16032 until revision H, and it wouldn't run our software, which wasn't of the most complex, until about revision J or K. And we weren't really conscious of that, apart from the annoyance that was going to be far behind everything else. Then we went and visited Western Design Centre, the designers of the beloved 6502. They were designing a follow-up processor, the 65SC816, so a hybrid 8 and 16-bit processor. Acorn would go on and use that processor for the communicator. Anyway, we went there expecting to find your standard tilt-up building full of engineers. We found a couple of bungalows on the outskirts of Phoenix, Arizona, staffed by a few quite experienced engineers and a bunch of essentially grad school students. And they were designing processors. It's just... there we are, that's the right slide for that. So they were designing processors. And that sort of coincided with Herman having a brainwave. Herman became convinced that if you couldn't design systems on silicon, then you wouldn't be a computer company. If you couldn't design your own custom circuits that you needed. So by this time, Acorn had built VidProc, SurProc in the BBC machine, the tube that connected the 2 processors together, and the Electron ULA. Have we built anything else? feels like I'm missing something. Whatever. So it was obvious that it was a key part of all our machines. So you could believe Herman. So he started staffing up to do that sort of build stuff. And then risk happened. I mean, it didn't happen much in the outside world, but Andy Hopper put on my desk the first papers out of Berkeley and Stanford, and about a week later, that out of IBM for the first 3 RISC machines, the Berkeley RISC-1, Stanford MIPS, and the IBM 801. IBM only published their work on the 801, which occurred first, because of the Berkeley and Stanford publications. So that was another lesson. Berkeley in particular had built this in a single year with PhD students. Maybe we could do that. So Project A started, and maybe we could indeed do that. I mean, you all know it happened, but we didn't. We kept expecting that there'd be some major roadblock that we'd run into, and that there was some secret magic that meant that we couldn't design a processor. Actually, that never happened. And if we were painstaking and careful, like we always were, that things could be made to work out. So it's often said that I designed the ARM instruction set, but it was co-designed. Steve and I and Herman was deeply interested in the progress of this and a very hands-on company director. You don't usually get to go down to the pub every lunchtime talking about your developments with the company director, but Herman was that sort of person. So we'd talk about where we'd got to in instruction set design, and if I'd wanted an instruction like add, compare and branch, and Steve had said, I can't make this work on the microarchitecture that I'm designing, you can't have that instruction. On the other hand, I said, I'd like a load multiple instruction, and Steve went away and thought, oh yeah, I can do that.
So add, compare and branch was briefly on the cards, was it?
There were no cards. The machine was mostly in our heads.
Right.
It was only later on when we had a fair agreement that we started writing things down for real. So
are there other,
on the brain cells.
Are there other good examples then of instructions that were kind of considered and didn't make it?
No, those are the big two. We did look at the other machines. So in particular, the MIPS had delayed branch with execute of forthcoming instruction. And we did not understand how to make that work. It seems obvious that if you get an interrupt, there's some horrendous situation where you're taking the branch and you're going to execute the forthcoming instruction, but you haven't even fetched it yet. And how does the machine correctly do that and return from the interrupt and not execute that forthcoming instruction, or end up at the branch 2 place or before both of them? And we couldn't understand how they did it, so we didn't put branch with execute into our machine. And that was probably for the good. As instruction sets got more complicated and the microarchitecture under them got more complicated, branch with execute became an impediment to speeding up machines. So not having one was helpful.
And I'm wondering what influences, were you looking at other instruction sets and kind of borrowing bits, having ideas? Something like the conditional execution on all instructions. To me, with my limited knowledge, that seems relatively unusual. Perhaps you'd seen that.
It was extremely unusual, yeah. And it was a big reaction to branches are going to take a long time. So if you have a pipeline processor and it goes fetch, decode, execute, which is the 3 pipeline stages of an ARM, ARM1, then you fetch the branch, you decode the branch, you execute the branch, you're going to have a 2 or 3 cycle bubble on every taken branch. And that was something that we didn't like. So my solution to that was to say, okay, we'll make all instructions conditionally executable, so you won't have to have a branch. So instead of saying if A is greater than 10, then move B into register 42. Well, it didn't have 42 registers. Move B into register 10. Then you could just say conditionally move 10 into B into register 10. And that was quite useful later on to ARM, because Dave Jagger at the back could then steal all those conditionally executed stuff and add new instruction sets to the machine. Essentially, I'd reserved 15/16 of the instruction set for future expansion without realising I was doing it.
And the pipelining, was that possibly should have been a question to Steve. I'm wondering if that was a difficult thing to get right.
Well, I mean, obviously building a processor and getting it right is a difficult thing anyway. So how do you build a processor and get it right? You test it. You test absolutely everything you can think of. So we have Hugo in here, who used to work for me, and is not in the least insolent at all. So we wrote programs that would test if the program execution was correct. So, assuming that something works and you can fetch an instruction, how do you test the instruction? So we wrote a large suite of self-test instructions for the processor. When Steve translated the machine into the next level down in the microarchitecture, that was divided into blocks. Every block needed to be tested separately, and then when implemented by Jamie's team, each test was carried out to make sure that every block was functioning correctly. And so when you reassemble the whole thing back into a working monolithic whole, then you're a happy bunny. If you don't test it, it doesn't work. Sometimes when you do test it, it still doesn't work. But definitely if you don't test it, anything that you've built doesn't work. And all the software engineers, well, certainly me, had that as an internal mantra. I used to collect programs that broke the BBC Basic Interpreter to make sure that as I fixed the bugs in the interpreter, they never came back. And so verification and validation, that's how you build stuff.
So I know there are a variety of simulators, and you had an instruction set level simulator. What kind of things were you putting through that, and how are you generating the code? Were you handwriting all the code? Were you already able to benefit from anything that Arthur was doing?
Well, we had the whole of Acorn's AR&D. Well, it wasn't AR&D at the beginning, it was AR&D as the project went on. So I had some people doing verification and validation, but the people who, like John Thackeray, who'd written the better version of the assembler that Acorn used, not my version, that got thrown away, but we moved from UAID to ASM and UASM.
And MASM.
And MASM, yes, when he added macros, yes. So the Thackeray's, David Seal, Axis started writing other stuff for ARM. So I was writing BBC Basic for ARM, of course. Why wouldn't I? As well as writing the instruction set simulators. But John and David Seal ported Lisp and Scheme in a very young fashion. Which of them wrote the BCPL interpreter? The compiler, I mean. So somebody grabbed hold of a BCPL compiler and got that working. As well as Arthur's compiler, there was another PCC compiler that was worked on. And then some folk in the computer lab ported Prolog and so on. So there were a lot of people trying to break it, as it were,
and these were all
use it.
Running on the functional simulator of one variety or another?
Yes, before the chips existed, the 6502 second processor or the 16032 second processor, if you wanted more memory, ran behavioural models of the instruction set, and so you could write these big programs. So it wasn't that I didn't know that ARM Basic would work when an ARM came along to actually run it. I was pretty sure that it was excellent, provided my instruction set simulator worked And to prove my instruction set simulator worked, we had the programs that Hugo and others were writing, and that they would run on the instruction set simulators. They'd also run on Steve's RTL model of the chip, and just a few of them ran on the actual RTL of the chip.
And did any of that influence?
Because that took ages.
That was days, presumably. Did any of that influence the instruction set? Were you making changes in response, or you kind of got it just about right first time?
I mean, I do it now. Verification and validation are so important that nowadays I change the instruction set of the machines that I design to make verification and validation easier.
Right.
I didn't do that for ARM. So it has some right swines for verification and validation, like the PC is an exposed register that changes dynamically. And that means some sorts of functional verification are really hard on ARM1. As ARM evolved, free of my malign influence, that sort of thing had to be fixed and removed because it's just too bad.
That's something I personally was interested in, actually, is whether there was an imperative reason for doing the whole machine state in one word, one 32-bit word, the compressing the PC down to 26 bits and using the other bits for flags and state and so on.
So ARM is an exercise in 32. So it has 32-bit instructions, a 32-bit data path, and 32-bit registers. And so it's nice if your PC plus PSR can fit in a register, because it means certain things are atomic inside the machine. So returning from an interrupt, you can change everything in one fell swoop, as it were.
A minor segue, since we've mentioned ARM Basic, and one of the volunteers here has posed an interesting question, which is, did Acorn ever think about licensing the Basic?
Yes.
And
it's one of Herman's great mistakes, and he admits this nowadays. So he held talks with Bill Gates. Bill came to Cambridge, and we went to the Garden House Hotel and discussed the things that Herman would like to exchange. So Acorn at the time had Acorn Ethernet, a working networked file system that was cheap and easy to put into computers, and it had BBC Basic, and it would like to investigate the process of selling those to Bill. He's moderately famous.
I think I've heard of him.
And for whatever reason, they couldn't come to an agreement. Herman says he was being too guarded. He should have come to an agreement. BBC Basic could have been even bigger.
Right. That's I've not heard that one before.
Well,
Okay.
things that don't happen are much harder to talk about.
Yeah. Where should we go from here then? We're running tight on time. I guess
We should press the right-hand button.
We've got a 10-minute countdown. We've obviously want to mark 3 o'clock.
3 o'clock.
Once I've started the countdown, you can carry on talking.
Right, so we've talked a lot about ARM, but it wasn't just ARM. We built a 4-chip set. The 4-chip set was designed to make a wide range of machines. So there was ARM itself, the processor, a memory controller, a video controller, and an I/O controller. So our little project, Project A, not only did it build working ARMs, they didn't go to production in that form. There was a bug. But we also built a memory controller, a video controller, and an I/O controller. And I saw Mike earlier today. He was in charge of the I/O controller. Steve was sort of in charge of the memory controller, and Cheetah Brown in charge of the video controller. So all of those chips, they're not perfect first time, but they all were capable of being used to debug themselves, and memory controller, video controller, and I/O controller went into production with the bugs still in, because you could work around them in software. So we made a large variety of machines. When we made the project public, Steve got journalists ringing up saying, you can't possibly have done this. If you had been doing something of this magnitude, I'd have heard about it. that was Dick Pounton, I think.
So we have to remember it was a very small group of people produced something really, eclipsed some of the other contemporary options.
Well, we'd thought, with all this risk stuff in our heads and reading the papers that came out of universities and research groups, we'd thought that this was really an obvious way to build a processor and everybody would be doing it. And that turned out not to be the case. It would take quite a while before any of the big companies espoused the principles of risk. We had at least a decade or more free of anybody producing a commercial processor in this sort of area.
And would you say that this is an example of a kind of vertical integration? You're making your own silicon, you're making your own operating system, not thinking of any other companies that...
Well, some of the operating systems, as we went along, did I skip past? No, I didn't. Come here. There we are. So when we got to ARM3, a microprocessor with on-chip cache, I think that's the first in the world microprocessor with on-chip cache, then we could build more powerful machines. So we ported Unix and made RISC-X and showed that we weren't very good at designing powerful machines. The project mantra for Project A was MIPS for the masses, with a subheading of keep it simple, stupid. And MIPS for the masses, we wanted to build something that would give performance to the common people rather than everybody else who was implementing processors, which was the highest performance possible, damn the cost. Yes. The bit that I wanted to talk about seems to be a long way down the slide set.
Whiz through them then.
So we kept going, and round about here, ARM, the company, departed the mothership Acorn, but we kept going. So why did ARM have to leave? You were too expensive to run, that's why.
It didn't feature in my salary though.
Yeah, it didn't feature in ours.
All the machines we got to actually do with the design on.
Yeah. So we couldn't support developing the chipset further. So we set up a joint venture and we built the world's first systems on a chip via ARM. So ARM 250, later on ARM 7500, were precursors of today's build a single chip, connect some memory to it and off you go approach. So this is ARM 250 built under contract by ARM Limited for Acorn, fabbed by Plessey, wasn't it? GC?
Yeah. By a contractor, Steve Temple.
And by Steve Temple, oh gosh.
And we're lucky to have on loan an example in the main part of the museum.
So they shipped a lot, and that was a problem because Acorn had kept 40% of the ownership of ARM, the company, which was fine. If you wanted to speculate in the success of ARM, you bought Acorn shares. Then ARM floated in 1998. Now you could buy ARM shares and sell Acorn shares. Ooh, sell, buy ARM. So this meant that the market capital of Acorn could be measured in terms of against ARM shares. So there came a time when Acorn's share of ARM was worth as much as Acorn's own shares are worth. Then it was worth more. Then it was worth more, including all possible taxes. And then it was worth more with a fabulous profit. The market valued Acorn and its technology negatively. So the vulture capitalists landed and offered to buy Acorn from its shareholders, and the shareholders were eager to accept. So they would be given 2 ARM shares for every 5 Acorn shares, At the time, two ARM shares were worth 4 Acorn shares, but they'd do it on 2 for 5 basis, and that would give Morgan Stanley Dean Witter a big profit. So Morgan Stanley Dean Witter had no use for Acorn. The whole of Acorn was just an encumbrance to stop them getting at the money that was embedded in Acorn's ARM shares. So they were happy to sell off the company. All the bits of technology that Acorn had developed over the years. So there was a set-top box market. Pace Micro bought all of that relevant technology from Acorn. And Element 14, a new startup, we bought the entire technology. That was good because I've been developing another processor. So I'm conscious I'm running out of time. So the computer side, it sort of trundles on. You can still get virtual Acorn machines, but the technology side, it says Acorn had been developing. I've been developing a new processor. So if ARM was an experiment in 32 with 32-bit instructions, 32-bit buses, and 27 registers, not 32, what would happen if I built a computer where the number was 64?
Do you mind if I start the countdown and you carry on? Is that
Yeah.
okay? Thank you. You can keep on talking. That's fine.
So if I took 64 as the number behind the computer,
You're not allowed to show any slides though.
now I can't share the slides, so you'll miss out on the pictures of firepaths and things. So with 64-bit instructions, that seems very generous for an instruction for a computer. So I made it occupy 2 to 4 instructions instead. So you have a 64-bit thing that the computer fetches as one go, but it contains 2 to 4 different tasks to do all at once. So it would run 4 instructions per cycle and was deeply pipelined. It was also packed SIMD, and it was aimed at DSPs. So at 300 megahertz, a Firepath would do 4 instructions per cycle continually without let up, and those instructions were packed SIMD, so each instruction was doing 4 to 8 useful things. So it was essentially giving us 60 to 128 operations per cycle of the type that we wanted. So Firepath became extremely dominant in the DSL market. By the time we finished, DSL has now been overtaken by fibre optic. We owned the entire central office DSL market. The company that, so Morgan Stanley Dean Witter had sold all the IP to us on a shoestring basis. Broadcom bought us for whatever it was, 680 million. So that just goes to show these financial guys aren't that smart after all.
Splendid.
Splendid. That was a bit rushed. There are some lovely pictures of Firepath.
And that I'm interested in Firepath doing it in software. Presumably, did anybody try to do it in hardware, or the standard evolves too much to? And that's a
yes.
a mistake?
So when we started in central office DSL, universally our competition were people with the DSL algorithms in hardware, and we were doing it in software. From 2003 onwards, we even did the FFTs necessary for the DSL in software. The first chip in 2001, we got an attack of nervousness and put an FFT block on. So each Firepath on the first chip was doing 6 lines of ADSL, but with the help of an FFT block. By the 2003 chip, when we'd really got our act together and knew how to write more software, we were doing 8 lines of ADSL 2+ per core without an FFT block. And at that point, people could just not catch up with us. Every time the standard evolved, we could rewrite our software, sometimes with performance loss, but we'd always be able to support the standard even with the chips that were already out in the field. And nobody else could do that. And for the things like packet header compression, what we called nitro in our marketing literature. Packet header compression could be done by the Firepath processor without any performance loss, and obviously gave you a better system overall. There was less bits going down the line.
Excellent. Lizzie.
We're just really keen not to miss
3 o'clock. Hopefully everybody knows this. We've kind of glossed over the 26th of April 1985, 3 o'clock.
It was on the slide, but
I think everybody must know. The processor came back and it worked.
the processor came back and it worked modulo a bug. So we had an instruction, rotate right with extend. Rotate right with extend worked, but there was a complicated situation for rotate right with extend when you used it in combination with another instruction that set the carry bit. The extend bit for the 33-bit rotate was in the carry bit. And so if you used the combination, then it didn't work. And we'd never tested that. So we tested that rotate right with extend would work. We tested that add with carry would work. And we hadn't tested the combination of those things. And that's where the bug in ARM1 was. So.
And I'll sign any ARM1 you've got if you want to. Slight tweak.
Yeah, so I mean...
I'm perfectly open about it.
Yeah.
It's all your fault.
It's my well, as you heard Sophie say, that we didn't test it either. It was doing the test program.
I thought my test did test that. But the point is, no one used it in real life because it's a slightly silly instruction. So everything works perfectly except the test suite, right?
Well, I did use it in real life. I was using it for the multi-precision shifts in BBC Basic. So eventually I could detect it when the BBC Basic interpreter gave the wrong answer. But that was well past me signing the champagne bottle.
And we had the further problem with the... if there was ringing on the lines, the chip would latch up because there wasn't enough protection on the bond pads.
Well, there wasn't enough protection on the bond pads to run the chip without a power supply.
And that probably is why, actually. Could have been. Yeah.
Did you intend to open the floor for any questions?
Yeah, we've got 5 minutes.
A minute or two?
3 minutes.
3 minutes. Go on,
You said you were doing earlier pre-using testing. You kind of did fuzz testing, kind of producing expressions to do it, or was it more you just thinking about stuff and doing that?
I didn't really get the sense of your question.
Well, was that something you thought about getting the machines to produce? Because you said you had
No, we wrote all our own testing programs ourselves. We sat there and thought, oh, how would we test that?
Okay.
I don't think fuzz testing was a thing at that point. It was
Yeah, we definitely
much later.
We definitely didn't do any generating buckets of random numbers and telling it to execute that to see what would happen, like I understand ARM does to an extent these days, just to check that nothing will make it halt and catch fire or seg unexpectedly or make a exception that isn't handleable, you know?
Yeah.
So yeah, there was no pointing it at somewhere random, unless we'd written a bug, of course.
So Firepath does have directed random testing, and I think ARM does as well.
In the BBC Micro and mini TV show, which are a wonderful cameo, there's the implication of that sort of Monday to Friday development period is that the spec you had was very close to what the BBC wanted. To what extent did you cheat to get to Friday?
We didn't. We built Proton. Homan had asked us to build the Proton prototype. We had no idea what the BBC's spec for a machine would eventually be, and they had no idea what our machine was going to be either. So following getting that, Chris Turner in particular, and me for the software, spent an awful lot of time liaising with opposite numbers, Richard Russell in my case at BBC, to get closer. System Basic at the time, for example, I'd taken out go-to line number. It went to labels, as it should do. And the BBC demanded that I undid all of that and put go to line number back in. I'm still aggrieved.
Here's more of a funny one. Did you know that someone ran DSL over wet string?
Some of the telephone wire in the UK is even worse than wet string. So you think of everybody calls it copper cables, but some of this stuff is on aluminium. So very lightweight aluminium lines. It's dire. So our modems have to constantly retrain themselves, because as the aluminium line blows in the wind, all its electrical characteristics change out of all recognition.
Yeah, I've affected her internet a few times.
We've reached a minute.
There we go. Right.
The opening of Eurovision.
Will you be singing, Hugo? Will you be singing?
No, I will not.
We've got a little surprise in the corner there, which we've turned the lights out. You might have to stand up at the back. One of our lovely volunteers, David, he's going to explain afterwards why he's done what he's done. But we can start a countdown quite soon, and then we'll be having champagne, and I might get you to spell out why we're doing the champagne as well, maybe.
Yes, by all means. Yes.
So perhaps when we get to 5, we can all start counting together.
Yeah, we're going to go for 5. Right. Here we go. It's coming.
5, 4, 3, 2, 1. Way!
Would you like to just say a few words about why you've done this?
Yeah, sure. So this is the 40th anniversary of ARM1. Thank you very much. Here we have 20 microbits. Now, you were talking about the BBC Computer Literacy Project, and the BBC have done the same thing again another 2 times with the microbit and the microbit next gen. And we have over 10 million microbits in the world, and there's 2 ARM processors for each microbit. There's a NOF51 and a CAR26. So we have 20 microbits, so that is 40 ARMs to celebrate 40.
About the champagne?
So it became a tradition, but this was our first go, that every time we got one of the Project A chips back and it worked, we would open a bottle of champagne. I'm teetotal, so I don't care. So it happened at 3 o'clock on the 26th of April 1985. It did not say, "Hello world, I am an ARM." That's, I think, one of Herman's apocryphal stories. But it did say pi, 3.141592653588979. 232,
Being
yes.
a much more meaningful workout of the processor.
Yeah. So the exact events were Steve plugged an ARM into an ARM second processor evaluation board, connected to a BBC computer. From a floppy disk, a copy of ARM Basic was booted. I typed the 2-letter command AB, because ARM Basic is called just AB, and the interpreter loaded and run. Well, at that stage I already knew that since the Tube operating system had booted up and we'd managed to load a program, that everything must be working. So I just wanted the shortest command I could think of, and that was p.pi return. It printed pi, we opened the champagne.
And I think it's worth saying that they're not here. The bottles that you have in the main gallery are the 4 original bottles for the 4 chips of the Archimedes chipset. And for a very long time, those were just on top of some cupboards at ARM. And I remember joining the company and seeing those. And very inspiring, very magical to see those, and a whole collection of subsequent projects. And I think it's I don't know, I think it's a tradition that we've slightly lost, he says, looking for...
We lost it when we got design centres on the other side of the plant, and then you clearly couldn't ship all the bottles to Cambridge and display them locally.
I think it's something we should try and recapture, start doing
now
again.
Selling chips again.
Very good.
Yes, Qualcomm won't let you forget that.
One thing that might be worth saying, since we're counting the number of arms, was 40 there. I believe the running total is something like 250 billion ARM processors.
300 billion chips powered by ARM processors, with multiple processors in each chip.
But what amuses me is there's been somewhere over 100 billion humans that have ever lived on this planet. So if you think about it, there have been more arms than arms.
Recycling the 1994 Robin Saxby joke.
As good now as it was then?
Yeah.
Actually, it was better this time.
So the first 4 champagne bottles, it was me writing on them. That's my writing.
I'm afraid we can stretch to 4 champagne and it'll go as far as it goes, and I'm sorry if you don't get it.
It was in pencil on one of them.
Here we are.
Oh, there we go.
Yeah, that's not
Sophie,
surprising.
would you like to sign another one?
Are we going to toast?
Anybody else who should?
Yes, we should.
It's very important.
Do you want everybody else to do one?
We probably will. You guys looking at the back? Special lemon.
Special lemon.
Grand Cru lemon. Quite right too.
Oh,
Right, well, so if you've got champagne, you're very lucky.
Yes, I'll stand up.
One,
Yes. If there's anyone who needs champagne is more
Yes.
deserving than I.
Is there anybody who thinks they
I
should
doubt it.
definitely have champagne? Right, well, here's to the ARM1 chip and its 40-year anniversary.
To the ARM1 chip.
and thank you very much to Sophie and to Robert for leading this part of the session.
Thank you. So today's a quick lesson in paying more attention, because I was at an event at ARM where we were unveiling a plaque on the building where